classroom. I'm sorry about that for the rest of the semester, so I'll update the pages to reflect correctly for that. And there might be problems with people trying to get in and out of the classroom due to this inconvenience. But just let us know if you have problems coming in here. Okay, so just to be clear about this, we have NUS students as well as guests. If you're a guest coming here, again, as I told last week, if you haven't watched the previous lectures, we expect you to take part in a class project that you'll have to do. So how does it work? Basically, within the next 3 weeks or so, you need to come up with a short project proposal like these two gentlemen. Yushan, are you here? Yushan is not here. Ziwei, are you here? Okay. Yeah, I think both of them have a class conflict, so they're not allowed to attend. They can't attend our section. But these are two NUS students who are doing a project as well. So I encourage everyone, even if you're from NUS, who is not an external guest, to do a class project. So what you can do is basically, again, pick some data that you have access to. It could be from a Kaggle competition or something that you have at your company, that something that you can analyze. Throw a convolutional neural network, one that you'll hear about in class, any of the architectures at it. Okay, and then be able to create a poster to talk about your results with the class, right? And as I said last week, actually the 231N group actually has a very nice set of projects that you can see from here. Okay, so you're welcome to take a look through all of the proposals here and then come up with something related or not. It's up to you. Okay, but at this point, we just want to get an idea of how many projects there will be, and you know, the number of posters that we can expect. So by again 3 weeks from now, we need you to submit a proposal, something like this. Okay, just saying what you're planning to do, and where you can put this is you can email me about it, but it's better if you do it in Slack so that everyone else can benefit from it. So what you can do here is you can write your project as a post, right? So you can post it or put a link to it in Google Docs, and then just write the details out about your data set, the algorithms that you'd like to investigate, etc., and put it up, okay? So you might get some feedback from me, but likely whatever you want to do is fine, because again, as external guests, there's nothing I can compel you to do, okay? But this will be a good discussion point for you to have a basis for checking with each other and understanding the material. And again, I want to emphasize, even though it's a lecture per se, whenever you're not sure about things, please ask, because there's so many people at so many different levels of experience. There are people here who've probably already done ConvNets in practice. How many of you are like that, have applied convolutional neural networks? A few of you. Okay, 1, 2, 3, 4, 5. Okay, and many of us who may not have any idea about it or haven't really understood the math, and that's fine, right? Because this is a study group course. Okay, so please don't feel embarrassed or shy to ask. This is the only way that we can level up as a group. Okay, so I will also try to be annoying to the presenters and serve the questioning role and ask a couple times, but I would like our designated questioners to fulfill that role. Okay, and just a note, because this is really a study group, you know, study groups also have social activities afterwards once in a while. So every now and then I will ask you if you guys would like to join my group for a social. So as I advertised on Slack this evening, my group is having a farewell party for one of our staff members, and it's not anything formal, so don't think you're obligated to do anything. But if you'd like to join us after this class ends at around 8 o'clock, you're welcome to go with us over to the Kent Ridge Guildhouse, which is 5 minutes walk across the car park, and have a beer on your own tab. Unfortunately, I can't afford, you know, stochastic gradient descent for everyone, but you know, you get the idea. So yeah, I think it's more fun for us to chill out and hang out than it is for us to absorb the lecture material, because it's always all there. It's already on the web and on YouTube. Okay, and without further ado, I think we have our presenter who will continue the work. Okay, so go up from there. Do you want to put it in full screen?
Yes.
Okay. So let's see, how do we do that?
Thank you, Prof. And thank you, Dev, Manu, and Ming for covering up the motivation for using convolution neural nets, as well as some basic technical details. So,
Okay, I'd like to add something on the previous discussion that we were having. We were discussing about why there are different final weight matrices for different filters in the convolutional network. So I guess the reason for that is because each of it has been initialized to a different value. So in the starting, we initialize it to a random value. And in the parameter space, when we do gradient descent, so each of those random initializations will descend down to a different local minimum. So I guess that's the reason for different final weight matrices and why they're not all same.
So we all clear about that?
Kernel by kernel, or is it like, say for example, you have a 5 cross 5 cross 3, right? So it's like 3 5 cross 5 filters. So does it learn 5 cross 5 as 5 cross 5 weights, or does it like learn when it's doing?
So as in for each like one filter size, there are many different layers stacked. So let's say we have 10 layers. So for each of those 10 layers, we have different weights. So for layer 1, there'll be a W1. For layer 2, we'll have a W2. So that each of these different filters will get activated to different features on the image. So
there's an example on that as well. We'll just go to an example. Yeah.
So actually, I have one more thing to add. Just now, I think Ming Ray, right? Yeah. You mentioned about the fully the convolutional versus fully conv network. I think you mentioned that FC network will give you require more hidden layers. Actually, I don't think that is right. So the reason why we use a conv network rather than fully connected, right, is because of the number of parameters required to represent. So actually, even with a fully connected network, right, by setting all the irrelevant weights to 0, right, you can just mimic exactly the same convolutional network. Right. So you don't really need additional hidden layers. Yeah. I'm not sure whether
actually, it's like
I think
additional hidden layers. I was referring to the exact same thing. So in order to simulate, let's say a 5x5 filter, then it's basically you have one neural net for top left-hand corner. Down there, you have another set of hidden layers for the next 5x5 grid and the next 5x5 grid, and you do that for every single 5x5 grid, and you repeat that for every single filter. And so it's like a million layers just to represent the same thing that convolutional neural net can do with just a few filters.
Okay, that's right.
Yes.
I misunderstood. Yeah.
So is everyone clear about that? Do we all know why we have to interleave the layers between convolution and radial? For nonlinearity?
yes.
Everyone knows. Otherwise, we'll stack linear on top of linear and we get back a linear out. Right. So there's no point in doing that. What about the pooling? Does everyone understand why we have pooling?
I'll be covering that.
Okay, so you're covering it. Okay, great. Let's go. Sorry.
So we earlier saw this example wherein we have a 32 by 32 image, which is convoluted with a 5 cross 5 filter, and which produces a 28 by 28 activation map. So basically, the size of the activation map depends on the size of the filter, the stride, as well as the amount of padding that we do to the image. So we'll take a smaller example and see how that's done. So assume a 7 by 7 image, which is being convolved with a 3 cross 3 filter. So firstly, this region of the image will be converted with the filter to produce a single output value. And if the stride is 1, with a stride equal to 1, this area, that is, we just shift the filter 1 tile to the right, and then again dot product with the image to produce another value. So once we do it with all the possible positions in the image, is with a 5x5 output. Why? Because of the width of the filter. Notice that the filter can start only at these positions. A position after this, because it will go out of the image. That's why it reduces the size of the output. Now, if we use the same filter with a stride of 2, it will reduce the size of the image further. We'll be starting over here first, then we'll be skipping 2 pixels, and then we'll be starting over here, and then the next we'll be starting over here. So basically what you'll have is 3 values for each similar thing for the column. So we'll end up with a 3x3 output. Now, one question: can we do this with a stride of 3? So if you see, with a stride of 3, the first position of the filter will be here, and then you skip 3 pixels. The second will be here. 3 pixels. You see that it has to start over here, right? So basically, you have some portion of the image which is not covered, and if you do apply a filter, the filter does not have enough data to apply it on. So you have just one row left. So we usually select this stride such that these cases don't happen, right? So now we come to some calculations. So if we have an n cross n image, and say the filter size is f cross f, the number of positions in which, just for now, assume that the stride size is 1. So the number of positions in which this filter can be placed on a certain row is, you can place it up till f over here, right? So f from the end, that is n minus f, right? So basically you have n minus f plus 1 for the starting position. So basically, if this stride size is 1, so you'll have n minus f plus 1 filters that you can place in each row. For strides greater than 1, you can just divide this n minus f by the stride size, because you are skipping that many pixels for each stride. So there's a simple formula which you can use to calculate the size of the activation maps. And you can see that the size is 2.33 for for a stride 3 for this particular example. It is not an integer, and we usually avoid such cases, right? So one important thing that we need to see here is that these pixels in the middle are sampled more times by the filter, right? So when a filter, say, assume this particular pixel, this pixel will be sampled when the filter is here, when it's here, when it's here, and when it's here, right? But say a pixel on the edge or on the corner will be sampled by 1 or maybe 2 or at most 3 filters, right? So there may be a possible loss of some information because of that. So to avoid such cases, what we do is we zero pad the image. That is, we surround the image with zero values. So what this does is, each pixel is sort of sampled equally. And also one more important case is that the size of the output sort of remains because usually the size of the output decreases unless we are applying a 1x1 filter, right? So if we are applying a filter with say f greater than 1 without zero padding, the size of the activation maps will decrease. So this sort of prevents that too. Yeah, so this is exactly the same thing. So we have a 7x7 input, and say we have a 3x3 filter. So you can see that you can place this filter 7 times over here. That's because instead of n, now you have n plus say 2 into the padding number. So basically your dimension now of the output will be n minus f, n plus 2p minus f. 2p is the padding that we add, divided by s plus 1. Right. So now with this formula, we can see that when f is equal to 3 and we zero pad with 1, the or when f is equal to 5, we zero pad with 2, or when f is equal to 7, we zero pad with 3. The size of the output does not change. That's because we can place those many filters on the image. Right. Yeah. So as I said before, if we do not zero pad, the size of the input layer keeps on reducing. Say, suppose we do not zero pad the image, 32 cross 32 input will be converted to a 28 cross 28 input on applying a 5x5 filter, which will again be converted to 24 cross 24 on applying another 5x5 filter. And so the number of values that you use to represent the original image keeps on reducing, and this might not be what you want, because it might not be able to represent the original image fully. And zero padding helps us avoid this. Yeah, so question time. Suppose we have an input image of this dimension 32 cross 32 cross 3, and we have 10 5 by 5 by 3 filters with stride 1 and pad 2. What would be the size of the activation maps? No. Yes. So how did we get that? So each. Okay, I'll explain. So now we have n equal to 32. We have f equal to 5, and we have p equal to 2. So what will be the size of each dimension of one activation layer? It will be 32 plus 4 minus 5 by 1 plus 1, which is 31 plus 1, which is equal to 32. Right? So we have 32 cross 32 I mean, an activation map has a dimension of 32 cross 32, and because there are 10 filters, there are 10 activation maps. 32 cross 32 cross 10. Yeah, we have an output volume size of 32 cross 32 cross 10. Right? Yeah. So another question: how many parameters do you need for these many filters? So you have 10 5x5 filters that act upon an input volume of 32 by 32 by 3. Yeah, pretty close. So basically 5 times 5 times 3 times 10. Yeah. So one more thing to note is that each convolution layer performs W transpose X plus B. So there is a bias associated with each filter. So basically it will be 5 times 3 plus 1 into 10. Right? So yeah.
Does everyone follow that calculation?
Yeah. So just to summarize the calculation of the dimensions of the output volume. So if we have an input volume of size W1 cross H1 cross D1 and a filter of size F, if we have K filters and we take a stride of S with P padding, the I mean, we just discussed the dimensions of the output volume will be calculated according to these formulas. Note that there will be the depth of the output volume will be exactly equal to the number of filters, because each filter produces one activation map. Right? Yeah. So some common settings, very popular settings that is used for filters is a filter of size 3 with S1 and P1. Notice that when S equal to 1, you actually don't need to worry about the filter size because this will always be an integer, right? But when S equal to 2, you'll basically have to fit these parameters in such a way so that this remains an integer. Right? So these are some of the popular settings for filter values, filter dimensions. One more thing to note is that 1 cross 1 convolution can also be used without zero padding, right? Because it does not change the dimensions of the output volume except for the depth, which is dependent on the number of filters that you apply.
Why would you use a 1 cross 1?
So
it says there, it makes perfect sense. So
yes. So basically, in a 1 cross 1 convolution, each filter you are just yeah. So you are accumulating whole of the depth volume into one single value.
Okay. Can you explain like what, like a concrete example why that would be the case?
Say, for example, you would want to calculate the average value of a certain pixel, right? So for that, the one, I mean, it does not take into account the spatial nature, right? It does it, but it sort of takes into account the different features that you have for that same pixel, right? So I mean, it makes sense in the sense that yeah, can be applied without any.
But wouldn't that be equivalent to just averaging out? I mean, why do you need a
I mean, that's
it's just taking the average of each.
Mathematically, it's identical, right?
Yeah.
Yeah,
So there's no
you're getting the
difference.
image back, right? You want to transform the image. I think you want the image back. But for example, let's just say it's 3. Red in the RGB.
Yes.
You're just getting the average of that value.
I mean, that's just an example. right? So you might want to infer something from the different features. So basically, this is an input image at the first stage, right? But later on, what each unit of this volume will represent is some sort of activation of some higher level feature, right?
To me, because
okay, so
for me, convolution is more like correlation, right? If you
Yeah.
have a one-time fund, you're not really correlating; you're just getting average. It's just
you're not
translate to a normal.
yes, you are not correlating
with the neighbor
with the neighbor pixels, but you are correlating with the features of the same pixel, right? So it works. It makes sense in that way.
So let's just summarize that. So if you're starting at the first layer where you have 32 by 32 by 3, applying a one-dimensional convolution would do something like what you're just saying, which is like getting the average grayscale value of a pixel. But at the deeper layers of the net, each layer represents something else semantically. It could represent whether there's a vertical edge or a horizontal edge or a certain texture. So when you do this one by one convolution, you're basically counting the average activation of all the features at that level, right? So maybe there's a particular part of the image that has a lot of activations because it has both vertical and horizontal lines, and some other part doesn't. So one by one convolution will capture that.
I think you're learning that one from one.
Yes, the
you're
weights
learning
are still being learned.
Yeah.
Yes.
That's a question. Why do we care so much about padding the edges? That isn't there the least amount of information in the edge? We should really care more about the center. So my second question is also, why do we convolve from the left upper right? Wouldn't it be smarter to convolve from the center? Because most of the image features are all in the center.
I mean, just because our intuition says that most of the image features are in the center, we shouldn't be excluding the information at the edges, which is sort of what you do when you don't introduce padding, right? So that's one point. Another point is that, as we see here, if we don't use padding, the size of the output volumes keeps on reducing, and we might end up with an output volume without, having so much less parameters that we might not be able to come up with a meaningful representation of the actual or meaningful features of the actual input, right? And coming to the second point, actually, we use this to convolve over all the possible configurations of this over the image.
Yeah.
Right. So it doesn't really matter where you start from. Right. If you start from here,
so if you have different image sizes or different sizes of inputs, then if you start from the center, you actually are looking at the distance of the features from the center. So that could be more consistent. Right?
I really don't understand the question.
I think that is incorrect in a sense, because it's like a convolution in some sense. You're just taking a look at like different chunks of the pictures, and the features within each chunk. It should be inconsistent with the location of where this chunk is from, because it's like the picture of a nose, whether it's on the top left hand corner or in the bottom right hand corner, it should still be the picture of the nose. And so it's like your network should still be able to like make this distinction and make this detection. And so it's like we're just separating the actual location away from the detection of such features. And also coming to the other point, it's like a lot of the our best and most latest networks, for example, the ResNet, contains like hundreds and hundreds of layers. So if you don't apply padding, what's going to happen is that your image is just going to keep shrinking and shrinking all the way until it's like you have a one by one single layer, which wouldn't really cause too much picture, and that doesn't really maintain the spatial structure of the original picture. And so what we do with padding is that we keep the structure of the original picture intact while maintaining it throughout the entire network.
So what I'm thinking about when I say start in the middle is because I'm comparing it to sorting algorithms.
Right.
So some sorting algorithms start in the middle and it's more efficient than starting at either end.
Right, that makes sense. But then it's like a sorting algorithm is capable of doing something like that. However, over here, in the domain of image recognition, it doesn't matter whether you start in the middle or you start on the top left-hand corner, because like what you're aiming to do is just to find the exact picture or do some sort of a localization, and that can exist on any part of the picture.
I think it's also related to the use case of the whole network. Why do we use a convolution neural network is to be invariant to those. So it doesn't matter if, because the use of convolutional neural network is not just to identify something in the center, but maybe it's used in identification of motion. So if you're applying it to a video, then a person is walking from one edge to the other edge of the frame. Then at each instant, the convolutional neural network should be able to identify the person. So it cannot bias itself to only look at a certain part of the image, but it should be invariant to the object where it is placed in the image. So that's why it's equal weightage to different all the pixels in the image, and not just to the center.
I think though your question is quite apt. I mean, from an efficiency point of view, if I had a fixed deadline about how many milliseconds I want to process, then we spatially know that the center of the image is probably more important. So it's maybe a good idea to like do the convolutions towards the middle and spiral outwards if you can calculate it that way. So that at least the middle part is covered within the time bound that you have for your application. That said, there's a lot of reasons why we want to do padding. As we already talked about, we don't want to shrink the size. But it's the case already that when we zero pad, we are in some sense introducing artifacts in our data, right? Because when you do the convolution, even in this case, we have this 3x3 grid, we're artificially introducing 5 extra values to this grid of 4 real values. And so our data at the edge is already somewhat tainted, right? But I think the lecturers in this course said that, you know, this zero padding, even though it's done, it doesn't affect the results too much because the artifacts stay at the edge. Whereas if you didn't pad at all, as you shrink the image, there's more resolution and more distortion that's happening at the edge of the image, and that's probably not very good either. So we've had to make sure that that distortion is minimized and just confined to the edge region.
Yes. So because of what is going on in this tutorial, there's kind of a disambiguation that we are moving this convolution from left to right, or as you're saying, center to outside. So basically what's really happening is we have, like, this is the image and this is the first layer. So basically there are n number of neurons which are calculating all of these in parallel. So we're not exactly moving the convolution, we're actually, each of this neuron is connected to some portion. And in the GPU, all of these is being calculated in parallel. So spatial of which neuron is being calculated, I mean, it's not exactly this. So that.
Right. So that answers your efficiency question. And another thing is that both of your points stems from a basic assumption that is not there in deep learning, which is your assumption is coming from the fact that a lot of information is there somewhere. More information is present in the center of the image or in some part of the image, and that is what you want to capture, right? Deep learning does not make such assumptions. That's the whole point of all the architectures and all the things that we are trying to do. The information can be anywhere, right? We let the machine figure out where it is, and convolutional networks specifically do that by. So in fact, the idea of adding zero padding is that we want to uniformly sample all over the place, and where more information is available depends on the application. Okay, so maybe if you are trying to detect images in a portrait, your assumption might be true, but that might not be the case. That you're trying to do some image recognition on surveillance camera, right? maybe the criminal is roaming around somewhere and that guy is there somewhere at the edge of the camera. So why would you want to make the assumption that center needs to be captured more? Right? Makes sense, right? Yeah. So it actually is actually more robust. Doing this way is more robust.
Yes.
Is there any, I know when you do filter size, it's mostly part size, one, three, five. And probably the intuition is to center around the pixel.
Yes.
But is there any case that people use two or?
So as Devmanu said, so there are certain, they have been tried and tested, and there are certain values of filters which have been found to give good results. So there is no restriction on using even-sized filters, right? But obviously, maybe a problem might require the the value of f p. So p mostly not. So the value of these are basically hyperparameters which need to be set beforehand. So these are. Huh? So they are values, I mean, which are found to do good, but maybe for a specific application a value of 2 might do better, just because in the image a size, I mean, you have more you get more meaningful features by taking a 2 by 2 field of view rather than taking a say 3 by 3, which might includes things that are not meaningful for the feature. Right.
I'd like to add something. So before deep learning, these convolutional filters were designed, and some of them are like, there is something called Fowell operators and Brevet operators in computer vision. So these are basically like edge detectors. So they detect the edges very well for edge detection. So they have certain rules empirically found out, like the whole weight should add up to something, and the difference between the corners and the column to column difference should be something that has been found out. So that difference, I mean, the edges are captured through that difference. Edges are nothing but the gradients. So the difference, as Devmanu said, there is a common area. I mean, if there is sky and there is something like a sea and there is a beach in that sense, so there will be an edge formed in between. So the pixels at this region will be different from the pixels in this region. So the operator will move around and do this dot product and sum it up. So that dot product can happen only if it is odd 3 cross 3. I guess if you can search for Fowell and Brevet operators, you can get it. Not sure what exactly is the value. It must be something added to 9 or something like that.
I mean, but we do not assume any kind of pre-knowledge about what values the filters should take. It's I mean, it's calculated by with the backpropagation algorithm. So the main idea is that you choose the filter size so that for a feature you get exactly the meaningful information, so small that you get the meaningful information, and not so large so that you introduce so many other pixels that do not have the information. So for example, say in this image you have a face, right? So you do not want the filter size to be so small that the whole face is not covered, and you do not want the filter to be so large so that many things other than the face is covered. So you want it to be sort of exactly somewhat the right size. So that is a hyperparameter which has to be set. So now we move on to how this convolutional networks relate to the neurons or brains, neurons in our brains. So as we saw in our previous in the previous lecture, that the neuron takes in all of the inputs and then weights it and then produces a function of that as an output. So in this case, a single neuron has a field of view. It does not consider the whole input, rather it just considers a patch and then produces an output according to that patch. So you can look at it as seeing a huge image and trying to see if there are some features in smaller parts of the image, and then just scanning through the image and trying to find out features. So basically the F determines the field of view of each neuron. The value of S determines the resolution at which you scan through. So say you have you have gone through a particular section of the image. Where do you see next? At what distance do you see next to recognize those features? That is what is determined by F. Yeah. So, and the different layers. So basically, you have different filters, right? So each so each filter you can think of as a different neuron specialized to finding a different feature. So basically, you look at the same part of the image, and you have 5 different neurons trying to figure out 5 different features of that same image. So that can be thought of as different layers in the output module. So this, any questions? Yeah, so we'll go. So the only difference between the convolutional view and the usual fully connected view is that a neuron in the fully connected in a fully connected layer looks at the whole of the input of the previous layer, whereas in the convolutional layer it only looks at sort of a spatial space at once and then produces an output accordingly. Does not look at full input, but rather it has a local view of part. So now we have these. This is a structure of the this is how a convolutional neural network looks like. We have a convolutional layers followed by ReLU layers to introduce nonlinearity, a bunch of those followed by a pooling layer, which is what we'll be seeing now. And then again, this is repeated for several number of times. And at the end, we usually have a fully connected layer to assimilate all of the high-level features that are there, that are produced at the previous layers, and to produce the final output. So, so with each activation map, the convolutional, each neuron generates an activation map, and so at each output layer there are several activation maps, due to which there are a whole large number of parameters. So pooling actually sort of reduces the number of parameters by doing some operations. One important thing to note is that the pooling is applied spatially, and it over each activation layers independently. that is the pooling over say layer 1 will not affect the pooling over layer 3, simply because you want to capture the importance of, so each activation map sort of represents a feature, a high level feature of the image, right? And pooling sort of reduces the size of these activation maps individually and independently, so that you have a single value for a specific region to represent that. So say for example, you have an image, right? Say this is an activation map, and say okay. So sorry. So the one of the ways we can do pooling is by so pooling is very similar to the convolutional filters that we use, except for the fact that instead of performing the dot product over a single output layer, say max pooling performs an average, a maximum of the layers. So for example, we have this value of the input image, and we have a 2x2x2 filter. So basically what you do is, with a stride of 2, so we take this 2x2 part, take the maximum value of these, and so basically we have this output generated from that. So now one might ask, why not say the average value? Why just the maximum value? So the answer is that you can use average pooling, but it is specific to, I mean it's again a choice that you have to make. But mostly what these activation maps denote are the activations of certain features, and what max pooling does is it sort of generalizes the presence of those features in this area. So it's better to choose the maximum value than an average value, just because say you have this activation map over here, and say you have a face over here, right? And you have to generate a single value for this region, right? So the activation map will have say 0, 0, 0, and a 1 over here, right? So if you want to say whether there is a face in this region, it's better to choose a 1 rather than the average of these values. So that's the intuition for using max pooling than using some other type of pooling.
Just make it a little bit more clear and connect with what the earlier discussion that we had, okay, right? So the idea of convolution, applying uniformly, putting convolution over all the regions makes sense with max pooling. Everybody is getting that, right? So earlier we were making assumptions that more information could be in certain part of the image and at certain other parts that are just sky, and we don't have to capture it, right? We don't have to make those decisions. We let the machine figure out where the important information is. That's what convolution is doing. The filters are moving all over the place, and there are several filters moving differently over different places. And you have a bunch of activations now, right? Now we make a decision as to which activations are important, which activations are, which regions are important, which regions are not important. How do you make the decision? The regions where there is the highest activation are the important regions, right? So how do you enforce that decision? Use a max pooling. That's it. Very simple.
For what kind of scenario
I'm not sure. I can come up with an example.
I mean, if you want to detect something that shouldn't be there in the image,
Maybe.
but yeah, even for that, you use max.
Yes.
Yeah, I think this convolution with the max pooling just makes total sense to me.
Shouldn't you find the most unique value? Is max pooling the best way to find the most unique value?
Highest activation. Highest activation. We don't know. So the whole idea is that we don't know which features work. Okay. So we don't design the filters in a with particular assumption as to this filter is supposed to edge filter, or this is supposed to be and has to capture some particular thing. We just randomly design filters with some sizes, right? But then once the filters do what it does.
Max pooling will give you all high numbers, right?
Yeah, correct.
Yes.
Most unique number rather than the highest number.
Getting a high number means the template matched with the image. So if the template is of an edge detector, getting a high number in the activation map means that that edge was found. Yeah. So that's why the high maximum value of an activation neuron matters, not the what is the number. Whether it is triggered or not matters. Triggered means that is found in the image. Not triggered means it's not found. That's why we try to retain the information of whether it was triggered or not, and try to lose the information of non-triggered values. And we do that over a neighborhood, just keeping a triggered information.
Basically, we are throwing away all the useless stuff that the convolutions have captured until now, and then we are taking the most informative stuff and passing it to the next layer.
So
that's how we are doing.
How many times can you have max pooling layer?
Good question, excellent question. Yeah.
Like because if you're because seeing it reduces the spatial resolution, right? As it goes, you don't want to reduce it really fast, or So how many times do you have it in a late?
So basically, it's advised to use a max pooling layer after a bunch of convolutional and ReLU layers, so that you have many features over there, and you max pool just once, so that over a certain region you take out the meaningful feature. Okay, and if you use max pooling again, it's analogous to just it's analogous to just changing the filter size. So if you have say a convolutional layer over here, and you have two max pooling layers.
Oh, that doesn't make sense at all.
No?
After max pooling, why would you have another max pooling?
Okay, so what was the
question? No, I'm asking, like, you have 3 con layers max pooling, then 2 con layers max pooling. So
how many times do you have?
Yeah, how many times do you have in, say, for example, you have a 9 or a 10 layer network, right? So how many times can you have these max pooling layers before it doesn't make sense?
I mean, usually there are it's a large number of times. It's a large number. So you have this, it's a hyperparameter.
The amount of information you want to keep versus the amount of compute power you have. So if you have a limited compute power, you want to reduce the parameters. So you reduce the parameters using max pooling. So if you have very less compute power, so you'll have to resort to having more max poolings.
Is it just based on the compute power then, or?
No, your richness of the image also matters.
So if you don't have max pooling, it will always be richer representation. If we don't use max pooling.
So max pooling, so it's a detector, right? The whole idea being convolution is that we are trying to detect something from the image. So how many stacks we have depends on how rich your data is, right? It's a trade-off basically.
What I'm asking is, suppose we have a really deep convolution neural network, right, and no max pooling layers, versus a same convolution network with max pooling layers, which is, and suppose we have infinite compute resource. Okay. Which one will be performed better?
I guess without the max pooling one.
Yes.
Not necessary.
No.
You need at least one max pooling layer, right? At least one.
No, I guess the point of max pooling is
just to reduce the number of parameters and keep the important ones.
Because without max pooling, anyways we have whatever we want. We have some extra information.
Yeah.
Anyways, it will not work.
Assuming that we have loads and loads of training data and infinite computing resources, I guess the ones without max pooling will work better because you don't throw away stuff. It's done by the
we can also
neurons.
Right?
Assuming that you have loads and loads of data and
keeping the noisy information.
Yes.
Yeah, you have to throw away noise. I think max pooling is very important.
Okay.
Max pooling as well as your dropout is necessary to ensure that your network doesn't overfit. Even if you have infinite training data and infinite computing resources, if you train on everything without anything and like just have thousands of layers of fully connected networks, your network will just overfit.
That's generally the case, as you want to prevent overfitting. So the max pooling allows your model to generalize more.
Yeah.
So you're reducing the number of parameters at the higher level before you go to the soft max. So
It's a classic trade-off. If you don't use max pooling, it overfits. If you use too much max pooling, it underfits.
Yes. Yes. Because max pooling usually, I mean, it determines the number of parameters basically.
So if you have less parameters, it won't be able to.
Yes, and if you have more parameters, it will overfit. Yeah. Right.
So when you look at the common settings, right, I think you can use max pooling a lot because if you use filter size is 2 and extract is 2,
yeah,
you will shrink your size into half.
Yes.
So you kind of need to max pooling a lot.
Yes. So usually max pooling is not done after every layer. It's done after, after a series of convolutions and ReLUs to just take out the. I mean, it's not performed too many times just because, as you said, if you do max pooling a lot, you sort of reduce the number of parameters too much and it might underfit. Right. So now, after a series of convolutions, ReLUs, and max pooling, we have to have, I mean, it's recommended to have a fully connected layer at the end of the network, 1 or 2 fully connected layers at the end of the network, so that it sort of has a whole view of all the features present in every part of the image. So as we know, in the fully connected layer, each neuron looks at all the inputs rather than just a spatial view, a local view of the input. So that is why we have a fully connected layer at the end of the network to help us make our decision by looking at all the features at all the places in the image. Yeah, so this is just a demo for the training of CNNs.
You want to show that? Do you guys have you all looked at this demo? Would it help people to look at it and play with it together, or you guys are all fine without it because it's past the 8?
But it's fun.
Okay, one click for 3 minutes or whatever.
Basically, it's just JavaScript. JavaScript is enough to make and convolution.
I don't understand learning rate. What's the learning rate?
I guess these change. Can I pause?
I think it's slow.
Yeah, it takes time, I guess. So, I mean,
It's running on the client side, right?
Yes, it's not running on.
No, locally.
yeah, it's running on this.
Huh?
It's running on the client side, yes.
Yeah.
Yes.
So it's going to be slow.
Yes. Yeah, so.
No GPU.
I mean, can run. I mean, I guess we'll just skip this. You can, yeah.
So learning rate, I think we'll get to later. It's basically related to how fast you're converging your W parameters.
Is there any lecture where they cover all the hyperparameters? That will be very useful.
I don't know. Actually, if anyone's watched all the videos, you guys can tell me. I haven't watched all of them. I'm just on the same week of the videos as you guys are. I watch them when I'm driving.
The following week, there's some small part on how you're doing hyperparameters, like you were doing research, that kind of thing. But I don't think they go really in details on the various hyperparameters they are. Like, they won't tell you how to tune the patch size of them. I mean, people write papers based on that. So
yeah, but what we do in research goes very quickly into practice and then goes very quickly into tutorials like the ones that present for people.
Yes.
So I wouldn't be surprised that while we're going through this course, that there'll be better materials out. So just as a class, you guys can all look out for materials and just put them on Slack because that will help everyone. So yeah, it will happen. I mean, you already know deep neural networks have only been around for what? I mean, the current peak has been around only for 5 years, so quite a lot of peaks have happened, and they will continue to happen. So it's good to keep up on it.
We did a tutorial at a recent workshop at NUS where we discussed about the parameter settings and stuff in great detail.
So you can put a link to your YouTube video.
Yeah. So I mean, if it was clear, if you are audible, then you please listen to it. But otherwise, I and NUS can do that part again in one of the classes. And that I think that will be useful.
So summarize.
Yeah. So in summary, in today's lecture, we took a look at how convolutional neural networks stack various convolutional layers, pooling layers, and fully connected layers at the end. They usually look like this, where a combination of convolutional and ReLU layers are stacked for some number of times, and then there is one pooling layer, and this whole architecture is stacked a very large number of times, followed by one or two fully connected layers just to have a high level view of all the features at the of all the high level features at the end, which is followed by a softmax layer to basically classify or have the probabilities of different classes, right? While this has been the traditional view, there have been recent advances in ResNet and Google Linet, which I guess we'll be covering in the next lecture or so, which don't use these architectures.
Can you say something about that third line? Trend towards getting rid of pooling and fully connected layers and just having convolution. Does any one of the lecturers want to give what that means?
Which one?
The third point.
Getting rid of pooling and fully connected layers and just using convolution.
There are papers where they talk about just FCNs, fully convolutional networks. I think it's for semantic segmentation. Some papers are there which is used, which doesn't have any fully connected layers. It's just fully convolution, and then you have it's like a convolution network followed by a decon network, and then you try to do the semantic segmentation. Like instead of just bounding boxes, it gives you the outline.
They actually in that fully connected layer, they reinterpret it as 1 cross 1 conv layer.
Okay.
And that is something. I mean, they didn't change the architecture, so the fully connected layer they reinterpret it as 1 cross 1 conv layer. That's what you told about.
Yes.
That. So just reinterpretation they change.
Okay. I mean, even if you do have a 1 cross 1 convolution, you're just looking at that pixel. Whereas a fully connected layer looks at all the pixels and all the layers together, right?
No,
you have everything connected to it. So
the fully connected layer is a spatial image, spatial structure, just unrolled.
Yes.
They just unroll it.
Right.
So instead of unrolling it, they just make it like I don't know. I'm not sure.
Yeah.
So I will agree with you that the 1 cross 1 convolution is different from fully connected. It is different. It's not equivalent.
No, that paper FTN for semantic. That's what they have done.
Something similar, but I don't really remember the details of that. But
can you post it into the channel on Slack and then say something about why it relates to this point? Okay.
So maybe it may be because of the fact that you just don't use pooling layers because now you have so much training data and so much computing power that maybe you don't worry about overfitting. That may be one case. If you have,
overfitting does not depend on computing power.
It depends on the size of the data set, right? If you have loads of data, right, and say you don't have many layers, many convolution layers. You have, say, I mean, a little less than. I mean,
no, but What is the issue with
so that you can control the number of parameters. Yeah.
But what is the issue with the fully connected layers? Why do you have to like really get rid of them? I mean, they say the trend is towards that, but what is the need for it really?
So I think it depends on the application. Really, for semantic segmentation or any segmentation, I would think that just
So I guess semantic segmentation, they are going to label each and every pixel. So they want to maintain that special structure, and they're doing end-to-end learning. So they don't want this linear structure.
Okay,
I mean,
so we'll take the rest of this offline. So if you want to have more deep discussion on neural networks, come with us to the bar. Otherwise, we'll see you next week. It'll be down here though. Okay, so you try your best to come to this location. If you have problems opening doors, just wait for someone who has access to open it.